Today we're going to talk about the Julia sets. We're going to start by looking at the Wikipedia page, and I'm going to show you what we're not going to do. Okay, the language surrounding the Julia sets was developed in the early 1900s, and the mathematical formalisms are, let's just say they're not pretty. It's a bunch of gobbledygook, and if you're not a hardcore mathematician, it's not going to make much sense to you. And so this is what I don't want to do. I'm not a big fan of the language. I'm not a big fan of the language of theoretical physics, quantum mechanics, relativity, and I'm not a big fan of the original language of chaos theory. And so let's just read a bit of this and I'll show you why. In the context of complex dynamics, a topic of mathematics, the Julia set and the fractal set are two complementary sets, Julia laces and fractal dusts, defined from a function. Informally, the fractal set of the function consists of values with the property that all nearby values behave similarly under repeated iterations of the function, and the Julia set consists of values such that an arbitrary small perturbation can cause drastic changes in the sequence of iterated functions. Thus, the behavior of the function of the fractal set is regular, while the Julia set's behavior is chaotic. Let's go down here a little bit and read a little bit more gobbledygook. Okay, let f at z be a non-constant holomorphic function from the Riemann sphere onto itself. Such f at z are precisely the non-constant complex rational functions that is gobbledygook, 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 gobbledygook. Okay, so I'm not a big fan of this language. I think that it's the mathematicians are making something very simple way too complex. Okay, this is a very complicated language to explain something very simple. Okay, so now let's go to the Wolfram Math World page and see what he has to say, or see what they have to say. Let R of z be a rational function where z is an element of the complex numbers and C star is the Riemann sphere, blah, 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 gobbledygook, gobbledygook, gobbledygook. So you're not going to like this. You're not going to like this, and I don't like this. I'm not going to explain the Julia sets to you this way. I'm going to explain Julia sets to you the way that I perceive them, the way that I discovered them in my own way. Okay, I didn't discover them, but I discovered my own way of explaining them. Okay, I'm just going to do one more. This one's a little more reasonable, by a guy named Paul Bourque. Okay, and this actually makes more sense. So, the Julia set is named after the French mathematician Gaston Julia, who investigated their properties in 1915 and culminated in a famous paper in 1918. Well, the Julia set is now associated with a simpler polynomial. Polynomial is just a function. Okay, so he used this complicated one, and I used the simple one, z equals z squared plus c, which you can see right here. Okay, so the Julia set is now associated with those points on the complex plane for which the series generated by this function does not tend to infinity. C is a complex constant. So in the z equals z squared plus c, C is a complex constant. Okay, and one gets a different Julia set for every C. And this was what I was trying to explain in a previous video, that every point on the complex plane generates a different Julia set. And I'm going to show you that right now. So here is the Mandelbrot fractal, the Mandelbrot set, And I'm going to show you how every point on the complex plane generates a different Julia set. So as you can see, as I move my cursor around, this is the complex plane. This is the complex plane right here. As I move my cursor around, I'm generating different Julia sets on the right-hand side here. And depending on where I go, you get a different shape. And so as I move in, to getting closer and closer to the event horizon, you can see the Julia sets. This picture is getting more and more complex. It's getting more and more details. Okay, so let's go back to the article. Okay, so the initial value, Z0, for the series is each point on the plane. And in the broader sense, the exact form, okay, there's a little more gobbledygook. I'm not going to read that. Okay, so basically what he's showing here is the same thing what I just showed you, is that each point on the complex plane generates a different Julia set. Okay, so here he says the well-known Mandelbrot set forms a kind of index into the Julia set. So he is saying that each point in the complex plane is an index for a Julia set. A Julia set is either a connected or disconnected. Okay, has either connected or disconnected depending on which value you select from the complex plane. So let's go back to my picture here. Okay, so basically what's happening is the points on the outside of the event horizon, what I'm calling the event horizon of the Mandelbrot set, generates a disconnected set. So these points are on the right here are disconnected. And when I pick a point on the inside, you get what they call a connected set. So basically the Julia sets from the inside of the Mandelbrot set, from the inner world of the Mandelbrot fractal, this figure here, okay, this figure here, generates a Julia set that has a central core, that has a nucleus, that has a connected region. And then out here you have a disconnected set, which they often refer to as a Fatto dust or a Cantor dust. Okay, so that is basically how a Julia set looks, and you can see very clearly that every point on the complex plane generates a different one, and that the Mandelbrot set, this is what I said previously in a previous video, the Mandelbrot set is basically a map of all the Julia sets. So I can tell just by looking at the Mandelbrot set that if I put my cursor in here, I'm going to get a connected set, a Julia set with a nucleus, with a black region. And if I put my cursor out here, I'm going to get a disconnected set. And as I get closer and closer and closer to the event horizon, you get a much more complex Julia set. Okay, so complexity increases as you get closer to the event horizon. So, so that's about it for the Julia sets. Now I'm going to show you something a little bit different that's related. I think I might have shown this before, but there is another way of rendering these points. So rather than generating a Mandelbrot set or a Julia set, what I can do is plot the trajectory directly. And so here what I'm doing is I'm showing, here's the real value and the imaginary value and the number of iterations. Okay, so here you can see I'm only doing one iteration, one iteration. Okay, basically the way the Mandelbrot set works is you pick a point on the complex plane and you iterate it through the function z equals z squared plus c, and you paint this color here depending on how many iterations. Okay, so you can see as I'm moving the cursor through this region, it only takes one iteration before the parameter, before the value escapes this boundary. So this outer black circle here is called the escape radius or the escape boundary. It is the escape condition. Okay, so then as I go in, so when I go into the next gray region here, you can see now there's 2 points, there's 2 iterations. So that means it takes 2 iterations. So all the points in this gray region take 2 iterations to escape this boundary. And as I move in, now it takes 3 iterations, 4 iterations, 5 iterations, 6 iterations, etc., etc. And again, as you get closer and closer to this boundary, the trajectory that I'm plotting as I iterate through the function becomes more and more complex. And actually, I'm just going to zoom in here a little bit and get a bit more detail on this. Okay, so you can see that as I get very, very close to this boundary, which is between inner world and outer world, between the black region and the outer gradient region, you can see the patterns on the right become more and more complex. And they kind of, it almost looks like they're exploding. Ooh, that looked really cool. See, there's one pattern that looks really cool. That is, this algorithm is set up to do 10,000 in 2 iterations, or 10,000 iterations, and I add an extra 2. So that is, this one has maxed out. Okay, it could probably go further. And as you can see, the patterns can become very complex, and also they look very cosmological. Okay, sometimes they look like galaxies, and sometimes they look like galaxy clusters, and you can see that clearly. I'm going to show you my Mandelbrot set as a quasi-black hole paper. In that paper, I show a bunch of trajectories here. So all the ones on the bottom are ones that I generated from the Mandelbrot set exactly using this method. Okay, and as you can see, the ones on the bottom I generated, the ones on the top are actual cosmological objects. And you can see that there are a lot of morphological similarities between these 2 sets of objects. Okay, and this is why I think, this is one of the reasons why I think the Mandelbrot set is related to black holes, because all of the objects up here are actually associated with black holes. You've got the Cartwheel Galaxy, you've got the Stingray Nebula, nebula explosions create black holes, you've got the Cat's Eye Nebula. All of these things are related to black holes. And so this is, you know, more evidence for me that the Mandelbrot set is related to black holes. Now here's another one. This one is quite complex. Okay, the one on the left I generated using this exact method. Okay, this exact method somewhere on this boundary. Okay, there's one that looks kind of like a galaxy cluster. There's another one. Okay, and so this is from my paper. So this exact point here, here's the real component. and the imaginary component, this one point is responsible for this whole galaxy cluster looking image right here, which looks morphologically very similar to the Virgo cluster. Okay, you can see there are a lot of similarities, like this doubling up of galaxies in the Virgo cluster can be seen in the morphology of this trajectory. This is one point on the complex plane generates this very complex, very noisy structure. If you can zoom in, you can see there's a lot of noise. There's a lot of chaos, I guess you could say, in this image. Not unlike what we see naturally occurring in nature. So this was my discovery. The fact that the closer you get to the event horizon of the Mandelbrot set, the more complex the morphologies, and that these morphologies look very much like cosmological objects. Okay, so that is just another way of rendering these points. You've got the Julia sets. And the Mandelbrot set. In a previous video, I said I consider the Mandelbrot set as the meta set. In that it is a map of all the Julia sets. So it is the superset, if you want to call it. It is the mothership, I guess you could say, of all the Julia sets. Okay, I know for sure that if I put my point in here, it's going to draw a connected set, and if I put my point outside, it's going to create a disconnected set. And that is what led me to think about the principle of incommensurability in relation to the Mandelbrot set, because there are clearly two distinct regions in the Mandelbrot set. Each region does something, completely different. They have different behaviors. They can be easily distinguished. They're not the same. Okay, and then you've got these points here. Now I'm going to tell you something about these points here that's really important. The points on the outside, the points in outer world of the Mandelbrot fractal, especially the ones really close, are expanding. They're expanding, and the points in here, when you iterate them, they're actually contracting. Okay, let me zoom in and get a bigger one here. So these points here, these trajectories, they're not points, but they're actual trajectories. They're orbits. They call them orbits. They are collapsing towards singularity. They're collapsing towards this point right here. Okay, so they can become quite complex too. But they are not expanding, they're collapsing. The points on the outside, they expand and explode. You can see they expand away. And the points on the inside, they collapse towards singularity. And so that is another reason that made me think that the Mandelbrot set is related to black holes. It's got a lot of the features of a black hole, a lot of the behaviors. Maybe it doesn't look exactly like a black hole in that it's got a strange shape instead of a circular shape, but it's possible that that we're mistaking this boundary for the event horizon when in fact the event horizon is way deeper in and not exactly what we think it is. So let's see, that's about it. One other thing, I wanted to show you the code for the Mandelbrot set and the Julia set, just to show you the difference between them, that the differences are not really that, there's not very many differences between the two algorithms. Okay, so to generate the Mandelbrot, and I will put this in the description so you can have a closer look at it. I'm just going to go over this quickly, and you can look at it more closely when you look at it yourself. Okay, so the complex numbers, as you may know from my complex number video, have two components, a real component and an imaginary component. Okay, so you need to generate the Mandelbrot set, which is z equals z squared plus c, you need a real z and an imaginary z, and you need a real c and an imaginary c. Okay, so you need actually 4 parameters to generate the Mandelbrot set or the Julia set. And you also need, when you iterate, you're going to be generating a new one. So the z on the left is going to be new, and the z on the right is going to be old, and you're going to feed the old one back in to create the new one. Okay, and also you need to, the escape radius of this guy, the escape radius is 2. So 0, 0 is there, and the distance from 0, 0 to this boundary is 2. Okay, it's kind of like the unit circle, but instead of being 1, it's 2. Okay, let's go back. So, and you need to decide how many iterations you're going to do. So max iterations is 1,000. Okay, and now I'm going to show you the Mandelbrot setup. So the difference between the Mandelbrot set and the Julia set is all in the setup. Okay, so when you set up to generate a point from the Mandelbrot set, you pass in the point. So you pass in the point, whichever point you are investigating. So let's say we're investigating this point here, minus 1.00137 and minus 1.48162. Okay, let's pretend we're evaluating that point. Okay, so that you would pass that point into the setup, and then these 4 parameters, the z real and z imaginary, constant real, constant imaginary, would get set to that point. So the variable z and the constant c get set to the same point. Now with the Julia setup, it's a little different. With the Julia setup, the z, the initial conditions, these are the initial conditions, the z real and the z imaginary are set to the current point, and then the constants are set to some other arbitrary constant. They're set to some, so the starting condition and the constant are different for the Julia set, and the initial condition and the constant are the same for the Mandelbrot set. So that's really where they differ. The iteration process for both the Julia set and the Mandelbrot set are exactly the same. Okay, you calculate, you put it through z equals z squared plus c, which is right here. Then you calculate a distance. So then when you run one iteration, you get a new point. You get a new point, and I'll show you that. Okay, I'll show you that. So when you run the iteration, you get a new point, and then when you run the iteration, you get another point, and you get another point. So if I'm iterating a point over here, when I iterate, I'm going to get 4 points. So I'm going to iterate 4 times, and each time I iterate, I get a new point. Okay, then what I do is I calculate the distance from that point to the origin, to 0, 0. And if it escapes, so if it escapes, if it goes out of this region, if the distance from the origin to my new point that I just calculated is bigger than here, okay, if it goes past, if it escapes, then I'm done. Then I'm done. And then I say escape is true. So if the distance is bigger than escape radius, I say escape is true. And if it's not, if it doesn't escape, then I put the new real value back into the old one, and I put the new imaginary value back in the old one, and then we iterate again. And we iterate again. Okay, so here is the function that I would call to do everything. Okay, so this is the main function, and I have the setup. So this is where you can see the setups are different. Okay, so I can either do the Mandelbrot here, or I can do the Julia here. If I'm doing the Mandelbrot, I just have to put in the current point. So basically what we do is to generate the whole Mandelbrot set, what we have to do is integrate over the plane, the complex plane. So for each point in the complex plane, we have to run this procedure. So I'll show you that. So for each point in the complex plane, so I have to integrate over the real part and then integrate over the imaginary part. Basically, I'm just picking points on the complex plane, running the setup, and then running the iteration process. The iteration process is just while the point doesn't escape, iterate again, iterate again, iterate again until it's done. And so if it eventually escapes, if we finally escape, then we paint, if it doesn't escape, this is wrong. If it doesn't escape, we paint the point black. If it doesn't escape, we paint the point black. Right? So if it doesn't escape, we paint it black. And if it does escape, we paint it a color depending on how many iterations it took for it to escape. And so that's the incommensurability of the Mandelbrot set. The points on the inside don't escape, and the points on the outside do escape. And the points in between take a long time to decide. The points in between are just not sure. Ooh, there's one that's really complex. The points right on this boundary here take a long time to decide whether they're going to escape or not. Okay, so that is all I'm going to say for now. I will put this little code, which you could, it's almost perfect. It's you could probably just take this code and cut and paste it and put it into a program and make it work. So I'll put that up in the description, and if you have any questions, please let me know.